Hi, my name is Abita Hawk, and today I'm going to be talking about my proposal, which is titled Ring Signatures Are Comprehensively Post-Quantum Secure, Even Against Active Adversaries. One thing you might notice is that there are quite a few terms here that I'm going to need to define to understand the proposal. Ring signatures, post-quantum security, and active adversaries. There are a few more terms that will appear throughout the talk that I'm not going to go into too much depth on, just enough to hopefully make this talk make sense on its own. But for more formal definitions, you can, of course, check out the written document. Here's just the outline of my talk, which is pretty standard. We'll start by talking about the context and problem. We'll talk about limitations of prior work, and then we'll head into my main contributions and proposed work. To start out with, context and problem, like I just said, and to understand the context, I will explain what a signature is. I'll talk about cryptographic security in general, and then I'll tie it all back into ring signatures and show basically what it means for ring signatures to be comprehensively post-quantum secure. All right, to start with, a signature scheme. I think a lot of people are familiar with the concept of a digital signature. Basically, a person here, Alice, has a public key and secret key pair, and she publishes the public key. The purpose of this public key is so that people can take signatures from her, and they believe in its authenticity. In other words, that it really came from Alice, and they believe in the message's integrity. In other words, the message wasn't somehow changed in the meantime. So anybody that has the public key can check messages and signatures. So when Bob is just going to receive the message and signature, which Alice signs with her secret key. And remember, he's got the public key. Now, finally, Bob has the public key, he's got the message, he's got the signature, and he can put them in this public verification algorithm and verify. And it just outputs a bit. So if it's 1, the signature is valid, it really came from Alice. And if it's 0, then it's invalid. And one thing I want to point out here is this is, again, public verifiability. Okay, so this is the setup for all signature schemes. And now we can think about what does it mean for the signature scheme to be secure. Okay, now that we know what the concept of signatures are, we can talk about how to build signatures. And the idea is in cryptography, you're building your house. So you start out with some foundation and you make some sort of assumption that you think is true in order to build signatures. There's lots of ways to do this. I think people are probably familiar with the concept of either discrete log or possibly factoring types of assumptions. So things like RSA. And here you say, okay, if RSA holds, then my signature scheme is going to be secure, and that signature scheme is created in a certain way. So in general, in cryptography, you just start with this hardness assumption, which I'll call P, and then you'll do a reduction. And the proof system is, the theorem is, if P is a hard problem, then my scheme is secure. And you're going to do this proof by reduction. So for example, you could say, if RSA is hard, then my signature scheme that I've built is unforgeable. where the algorithms for gen and verify and sign have been specified in some particular way. The new information that we have here is this concept of a reduction. So let's look at what that means next. Now that we know what a signature is, we can extend it and talk about ring signatures. As before, we have some public keys, but here, now we're going to talk about a set of public keys where each user knows their own secret key. And what a signer is going to want to do is they'll use their secret key and the knowledge of everybody else's public keys in the ring to create a signature that verifies on behalf of someone in the ring. Since it verifies on behalf of someone in the ring, we still have the notion of unforgeability like we did with signatures, and now we have this concept of anonymity within the set. These are the two important security notions in ring signatures, and the way that it is defined can be quite tricky. In other ring signatures works, and yes, there are a lot, the security is defined by using a game. There's an adversary who is allowed to have access to these different oracles that mimic the behavior of what would happen in a ring signature scheme in reality. Now, most ring signature schemes do allow an adversary to ask for all the signing queries it wants, but not every scheme allows the adversary to generate new keys. In some cases, the keys are set at the beginning of time, and the adversary can only ask signing queries on those. A lot more schemes don't allow corruptions of honestly generated keys, and a lot of times, of course, they don't allow registration, where the adversary can actually create their own keys and add them to the ring. So this has been a limitation of previous ring signature schemes, and it didn't seem very comprehensive because ring signature schemes, the way that they're set up, allow a user to just add themselves. They can just create their public key and their secret key, and they can just publish it and say that they're part of a ring now. And anybody can use those keys in order to create a ring signature. So it seems especially important that you could have malicious users, and therefore these corruption and registration queries become especially important. Now that we know what ring signatures are, and we know what security means in the context of ring signatures, we do need to tie it back to a few more keywords that appeared in my main statement. Ring signatures are comprehensively post-quantum secure. Here, by comprehensive, I wanted to include some variations of ring signatures. There's threshold ring signatures, otherwise known as Thrings for short, and there are traceable ring signatures and linkable ring signatures. All these do are take the original base definition of ring signatures, which just include unforgeability and anonymity, and it adds some extra requirements that we'd like our ring signatures to achieve. I'll talk about those in the upcoming slides. Last, I am going to talk about what it means to be post-quantum secure in a little bit more depth in the context of ring signatures. The first variation of ring signatures I want to talk about is Thring signatures. In a Thring signature, rather than having 1 out of n sign the ring, you can now have t out of n for some threshold. There are 2 different ways to achieve threshold ring signatures. One is by having interaction between the parties, where each of the signers here are going to work together somehow to create a combined signature that looks like it used at least 2 different secret keys. And another way is by having intersigner anonymity, which means that each signer could individually create their own signature, and somehow these together will verify as having come from different people. This is not possible to do with the base definition of ring signatures because they're truly anonymous, and so two signatures could have come from the same person twice. I want to give some more detail about interaction between the parties. So here we have our two signers, and they're going to work together to create the signature. They might have to talk to each other because only they know their own secret keys, and they've agreed on this message and ring to talk to each other on and produce the signature. Once they're done, they will put it together and create the signature and ring and send all that over to the verifier. But this has the issue that these signers have to at least know each other's identities. Next, I'll talk about intersigner anonymity. Here, as I mentioned before, you can have a list of signatures, and there's some way to tell that these signatures actually came from different people. So in the example I have here, let's say sigma 2 and sigma 3 are here, and you can take this pair and you can link them if they are on the same message and on the same ring. And it will either produce 1 saying yes, they're from the same signer, or 0. This has an aspect of linkable anonymity in that you can tell that it came from the same signer, but you don't know exactly which signer it came from. There's another way to do this with trace, and trace is similar, except if it came from the same signer, it will actually reveal the identity of that person, or it'll tell you that they're independent. So in this case, the signer's identity is actually revealed. In other words, there's some way to tell from the two signatures whether they came from the same signer or not. One thing I want to point out is that traceable and linkable are slightly different notions than intersigner anonymity. The definition that I had for linkable had the same message and the same ring because that made sense in the context of Thring signatures. But there could be other situations where you want to be able to do a link rather than on the same message. You want to have possibly two different messages, possibly two slightly different rings, and two different signatures, and it should tell you whether these two signatures are linked or not. And similarly for trace, the input can be extended to be for different messages and different rings like this. That might be in the case where you want somebody to sign only one time regardless of the context. So traceable and linkable are a little bit more stringent than intersigner anonymity in that sense, or more generic. So one thing I want to point out here is that by limiting the definition, you can get intersigner anonymity. But I want to avoid, in the case of intersigner anonymity, different messages or different rings actually outputting 1 or 0. So there's a little bit of a play off here. To prove that ring signatures are post-quantum secure, I need to show ring signatures that are built off of post-quantum secure problems. So earlier I gave this list of different problems that crypto systems can be based off of. And some of these are now gone because it turns out that they're not post-quantum secure. So it turns out discrete log and factoring are out and pairings are out. However, some specific problems like lattices and LWE, ring learning with errors, these sort of problems remain, to our knowledge, post-quantum secure. Those are specific problems. We also have the general assumptions like hash functions and one-way functions. And as long as these have a specific quantum version of them, then they will remain secure in the post-quantum setting. So we're kind of back to where we started, only I just put in the qualifier post-quantum everywhere. If P is a post-quantum hard problem, then my scheme is post-quantum secure. Earlier, I had the example that if RSA was secure, then my signature scheme would be secure, and that no longer goes, but I could just say, oh, what if I just use LWE to build my system? Can I just prove that my scheme is secure as a result? The answer to that is mostly yes, but there is one more subtlety that goes in here, which is my proof needs to be post-quantum as well. With these game-based proofs, we have this adversary that gets some sort of view, and we can give inputs and outputs, but now this adversary may have on the inside some sort of like quantum computing that it's doing, and that already makes a difference. Furthermore, we might want to have quantum communication. So these inputs and outputs could become quantum in between the reduction and the adversary. And these proofs become a little bit trickier to do if you make these kinds of requirements. The last thing I want to talk about in terms of cryptographic reductions is the concept of model. A lot of proofs in cryptography are done in the random oracle model, or ROM, which is an idealized model of cryptography. This is in contrast to the plain model, which is heuristic and falsifiable and includes problems like LWE or RSA or things like that. The random oracle model often makes things a lot easier because it assumes totally random outputs on an input. It assumes that this idealized hash function exists. And if things are totally random, you get a lot of other nice properties out of it. That's a lot easier than dealing with specific assumptions that have a certain structure that you have to make sure to be careful about throughout your proof. However, in the quantum setting, there are some subtleties that make it so that even proofs in the random oracle model don't go through. In the classical random oracle model, you go input, you get a random output. So for each input, there is a random output, so X to Y. But in the quantum setting, if you want to allow quantum queries to the random oracle, you can have a superposition of different inputs, kind of like a probability distribution over all of the possible inputs that you could give to the random oracle. And that random oracle will actually give you back a superposition of all possible outputs. And this simple change, where it's a probability distribution rather than just input-output, makes certain proofs in the random oracle model not be valid if they're in the quantum setting instead. At this point, I've given the background and context of the landscape of ring signatures, and now we can talk about specific work. So now we're at limitations of prior work. Previous works can have different issues with them, and we look for those gaps and try to fill them out. One issue that can happen is that the ring signature may not be efficient. If you have n ring members and you have a size O of n ring signature, this is not considered very efficient. It would be nicer to have O of log n. Another limitation is that previous ring signatures did not have active adversaries, as was mentioned earlier. And I also alluded to previous ring signatures did not explicitly prove their work with quantum reductions, namely with the quantum random oracle. Finally, previous ring signatures did not have explicit post-quantum security definitions. So that puts me to the placement of our work. First, we need to have specific definitions that do what we want. We need a formal definition of what events can occur, and we want to capture active adversaries, and as well we want to capture post-quantum adversaries. Next, once we have those definitions, we need to come up with a construction that satisfies the definitions. And so there's going to be different parameters and assumptions that go into those constructions. So the assumptions, of course, we need to have hardness problems that are post-quantum. And another thing, of course, is that we need to ensure that the reduction is post-quantum. And with that, we would be able to create a ring signature that satisfies these stronger definitions, thus showing that ring signatures are comprehensively post-quantum secure, even against active adversaries. The last thing to deal with is you want to make sure everything is parameterized correctly. So when we talk about our hardness problems, we need to deal with how many bits of security we want to get out. So we do need to be specific, and that has to do with the specific construction that we use, and that will become apparent throughout the proofs. And that's where we can talk about the different inputs to the ring signatures, like size of the ring, size of the threshold, how many bits of security you want, in terms of computational security, maybe concepts of statistical security as well. Now, finally, we're at the point where I can talk about my contributions and how I would like to answer some of the limitations of prior work. I want to list out what papers I have. There's basically 2.5 here. The first one is compact Thring signatures in the plane model, which I refer to as log Thrings. And the second one is post-quantum Thring signature scheme proved in the quantum random oracle model, which I refer to as PQ Thrings. Lastly, I have in progress a post-quantum traceable ring signature scheme that's proved in QROM, and I call that PQuats. So these are some papers that try to address some of the questions that we saw with limitations, but there are still more questions to be answered. Let's delve into that. Let's talk about post-quantum ring signatures and what's been done and what there is left to do. In my work with threshold ring signatures, I am the first to provide proofs in the quantum random oracle model of a ring signature scheme. So other works that do claim to rely on post-quantum hard problems still have a limitation and didn't prove their schemes explicitly in a quantum reduction, and mine does. But there is still a limitation in that I do not yet allow quantum communication between the parties. Meaning the adversary has on the inside a quantum computer, but he's still required to make classical queries and receive classical answers in return, except for with the quantum random oracle. And it seems that we should expand this by allowing for different oracles to allow queries in superposition. So we looked at the work from Scafro and Zhang from Asorix, which is one-time traceable ring signatures, and this scheme is much simpler than the one that I provided in my paper, and it still lacks the quantum definitions and quantum random oracle model, but because of the simplicity of the scheme and what security assumptions it makes, it seems like it should be relatively easier to take this scheme and put it in the quantum random oracle model and provide these more comprehensive quantum definitions that allow for quantum communication. So left to do would be to take this scheme and to make it quantumify maybe. And along with that, we notice that this paper, of course, like I said, is much simpler, but it has a similar structure as the one that I provided with my Thring signatures. So there is also a sense of generalizing the papers and saying that in general, if you follow the Thring signature paradigm that I provided, you can actually get a comprehensive quantum secure ring signature. So what I have done with ring signatures is Intersigner Anonymity with ring signatures is I have work called logarithmic size threshold ring signatures in the plane model. So we have been able to achieve logarithmic size, also known as compact ring signatures, meaning that it's O of log of n, where n is the size of the ring. And we are in the plane model. However, there is a limitation to the scheme because of our insistence on being compact and being in the plane model. We end up with a weak definition of unforgeability. And there didn't really seem to be a way to get around this. It seemed that in order to be able to prove that our scheme was secure in the plane model, we had to have an unforgeability in which the adversary could not access the registration oracle. And remember how I said earlier is that it seems that this is not realistic. So the question is, to do, we want to have a compact ring signature or a Thring signature, have it be in the plane model, if possible, but achieve unforgeability that allows registration. This might be too stringent, and so it does seem that we might be able to give up on the plane model and go into something called the CRS model, in which case it seems that it is possible to achieve the good unforgeability, and this might have to be a trade-off that we'll make. So the first sub-question was, is it possible to do this in the CRS model? It does seem so, and then the second question is, can you modify this this ring signature scheme and see if it works in the plane model? The last thing I want to talk about is bonus, which is not ring signatures, but the concept of anonymous authentication or 1 out of n ring signatures, and how those could apply in different settings like group signatures, which do have trusted managers. So I have a paper that applies these kind of group signature style authorization to a cellular network. Here, there's not really anything active to do other than to, at each point when I'm working on the ring signature schemes where I'm trying to fix my limitations, consider whether it would apply in the group signature setting kind of for free. And that's kind of nice because it'll show extensions of my work and probably provide a lot of useful, interesting future directions as well. So now that we know the limitations of my work, we can go into the research questions. The first question I have is, can we have a compact Thring signature that allows for users to maliciously register their own keys? Log Thrings missed this, but it had the nice property that it was in the plane model with no trusted setup. So the most desired outcome would be to have a Thring signature that allows malicious registration in the plane model with no trusted setup. But we do have a failure mode or a simplified mode, which is how do you get these kinds of compact Thrings if we do allow trusted setup, and showing a specific construction of that. The next question is, how do we make a compact traceable ring signature that's possibly in the plane model? So with the work of Scafuro and Zhang that I mentioned, it's a one-time traceable ring signature. It is not compact, and it's also only one time, and we would like to make this generally traceable. So that's the next question that we'd like to answer, is how to generalize on that previous work. Third, can we allow a post-quantum secure ring signature scheme which allows all oracles to be quantum? As I pointed out with PQ Thrings, this was a limitation. Only the random oracle was considered quantum, and that's something we want to improve on by my work on PQuats, which should allow more general, comprehensive post-quantum access for the adversary. And then finally, the bonus question, which is just stuff that we'll hopefully get along for free along the way, is if you have ring signatures which don't have trusted setup, how do you apply these in a less stringent setting where you do have a trusted manager or some sort of setup? And that's it. Thank you.